work, and all of the reference numbers that I give throughout this talk are going to be referring to the reference numbers in that paper. Okay, so here's some of the organizations that sponsored this work. Okay, so this work is all about ways of trying to make quantum computers more useful towards the goal of simulating physical and chemical systems. So we all have this long-term goal that it would be really great to simulate large, strongly coupled quantum mechanical systems. We're far away from doing that. And one of the reasons why we haven't been able to use quantum computers to simulate quantum mechanical systems that we couldn't already simulate with a classical computer is because the quantum computers are too noisy. So what that, Una, would you mind muting yourself?
Oh, sorry, I'm sorry.
So one of the, example algorithms that we might want to run when we talk about like physics and chemistry problems is something called the variational quantum eigensolver. And this is going to be the algorithm that we kind of have in the back of our minds throughout this talk, although the things I say might be relevant to some other things as well. So variational quantum eigensolver is, like suppose you want to find the ground state of a Hamiltonian and you want to put the quantum computer in that state. VQE is sort of a near-term and something that we can implement now way of doing that. The idea is that you have some ansatz circuit, which is parameterized by these parameters theta, and you get to pick what this ansatz circuit is. And then you run the circuit on the quantum computer, you measure the energy, you feed that back into the classical computer, and you adjust these the parameters theta using some classical optimization routine to try to get as close to the ground state as you want. So it's the normal sort of variational approximation to a ground state that you might have learned in your quantum mechanics class, maybe to approximate the ground state of helium, for example.
Excuse me.
Yeah.
This is same here. My video's on. So this is gradient-free optimization. Is that right?
So actually, you could compute the gradient using the quantum computer, but you could do either.
Okay. So in practice, I know gradient-free optimization is hard. Can you comment on like which way would work? I mean, if you measure the gradients, that means you have to compute again as many correlations, as many observables as you have parameters, right?
Yeah, that's right. But maybe it'll converge in fewer steps if you do that. So
okay, so you don't have that particular implementation in mind right now.
So when I ran this, we didn't compute the gradients, but there are ways that you could compute the gradients using a quantum computer. So you could do either.
Okay. Thanks.
And so there are also other ways of finding ground state. So there's something called quantum phase estimation, which is a way of, like, if you can implement a particular time evolution operator that's the exponentiation of a Hamiltonian, then this will it's essentially measuring the energy. The result of this procedure is that it puts you into an eigenstate. And if you start with a significant overlap with the ground state, you could find the ground state that way. But quantum phase estimation is a more long-term goal because it requires deeper circuits. And so we're going to have this sort of thing in mind. And so here's an example of this is from our paper. So we implemented VQE on an actual quantum computer. And so here we're approximating the ground state of the mixed field icing model on 20 qubits. And we pick an ansatz. I'll show you later what our ansatz looks like that has 3 layers. And you can see it converges towards the ground state. Now, the blue dots here are the actual results of the measurement from the quantum computer, and that's the thing that we're feeding into the optimizer. The yellow dots are instead feeding the same circuits into a classical simulator. And the reason that they're not right on top of each other is because of the noise that I was talking about before. And you can see that the effect of this noise is sort of to damp these measured energies towards 0. And I'll say more about that later. And another point, which I'll also expand on more later, is that you can see that the optimizer is more or less converging, even though it's only seeing the noisy values. And as Sam mentioned, there are various ways that this could go wrong. One is just if there are too many parameters and the optimizer has trouble converging. That can happen. Another thing that could happen is your ansatz might not be expressive enough to capture the ground state. Excuse me. So you might need to make your ansatz too deep, and the deeper your ansatz, the more noise you have. Because when I say the depth of the ansatz, I mean like how you can think of that kind of like runtime, and the state decoheres or drifts more as you apply more gates and as the runtime is longer. Here's some qubit diagrams of the actual quantum computers that we used. And in particular, this loop in the middle, this one is 20 qubits, which is why we picked 20 qubits. 20 qubits. And these connections here indicate that we can apply a gate between those 2 qubits. So you can't apply a gate directly between qubits 10 and 11, for example. You would have to instead apply a sequence of gates between the qubits that are connected. And whenever you apply a gate, the gates are not perfect. This is a major source of the noise that I was talking about. So the 2 qubit gates, which are these controlled knots, they fail like 1 or a few % of the time, as you can see here. And also, whenever you read out your measurement at the end, that also has some noise, and you get the wrong answer something like a few % of the time. And that also varies depending on which qubit you're talking about. So this is why it's so noisy, and these errors, especially the 2 qubit gates, they compound when you make your circuit deeper. So there are 2 things that 2 broad strategies that we might try to do to approach this issue of noise. In the long term, the community wants to implement error correction, in which logical qubits are encoded in multiple physical qubits, and you can kind of correct the errors as you go along. That's expensive, though, in the number of qubits, and we're not really at the threshold for being able to do useful error correction yet. The more near-term approach is instead called error mitigation, where error mitigation is a term that encompasses lots of different strategies for trying to undo the effect of the noise without doing error correction. And so here's some well-known techniques for error mitigation, or relatively well-known. So this idea of zero noise extrapolation is, suppose we know how to artificially increase the noise in all of the gates. Then if we're computing the expectation value of some observable O, and let's say this axis is the noise, and we start over here, this is like the normal amount of noise, and we artificially increase the noise, then we can extrapolate back to 0 and say, okay, this is like what it would have been without the noise. So that's called zero noise extrapolation. Probabilistic error cancellation is, well, you do full gate set tomography, meaning that you take all of your noisy gates and write them in the basis of the ideal gates. You see, like, what are these noisy gates actually doing in terms of the ideal gates, and then you invert that matrix, and you write the ideal gates in terms of the noisy gates, and then you can write your ideal circuit as some linear combination of circuits that you can actually implement in terms of these noisy gates, and then you sample from those circuits using this quasi-probability distribution idea. So that's this one. This idea is, suppose that you have some circuit that you want to run, and you just make multiple copies of it. So let's say we make 2 copies of it, and then you can entangle these copies in such a way that you can measure, you essentially take powers of the density matrix. So so you can put the thing in a state that's rho squared instead of rho. And the idea is that if you write rho in the basis in which it's diagonal, then these are the different probabilities of the different pure states in that ensemble, etc. And the state with the highest probability should be the ideal state that's like the outcome of the circuit that you want. And so if you take powers of rho, you suppress these other states, and you make your mixture closer to the state that you want. But our paper is actually not about these techniques. It's about a different class of techniques. And these all are based on the following observation, which is that the effect of the noise on the expectation value of observables is generally to damp it towards what that expectation value would be in a maximally mixed state. So this here is the expectation value of the observable in a maximally mixed state. And the important point here is that this thing is generally known, and in our case it's 0. And so if you know what this damping factor is, then you can invert this equation and you can get your exact expectation value in terms of the noisy one. So for us, you just have to divide by C. Now that's great. We've taken this problem that seems very complicated at first, of like undoing quantum noise, and we've reduced it to estimating one parameter, which is between 0 and 1. The problem is now we have to estimate that parameter. So there are a few different methods that have been proposed for estimating this damping factor. We talk about a few more methods in the paper, but I'm going to focus on these 3 because these work the best out of them. And I should say that proposal 3 was one that we came up with, and proposals 1 and 2 here were proposed by previous papers. And one of the authors for this paper was Ben Nachman, who was an undergrad at Cornell. So let me talk about method 1 here. So this was kind of mentioned in a larger paper by the Google team. And the idea is, suppose that what you're trying to simulate is a Hamiltonian that has a perturbative regime, but you're also interested in studying it outside of the perturbative regime. And in particular, I mean, studying the perturbative regime on a quantum computer isn't particularly useful because it's perturbative, you could just calculate it by hand. Whereas the quantum computer might actually teach you something outside of the perturbative regime. And so the idea here is just use the perturbative regime to measure what this damping factor is. You know what the exact expectation value of your observable is from the perturbation theory, and you know what you get when you measure it on the quantum computer. You can divide those and get the damping factor. And then you assume that the damping factor is independent of this coupling J, which that's an assumption. And then you can use the damping factor that you measured in step 1 here and do error mitigation outside of the perturbative regime. And in this Google paper, they were mostly talking about, like time evolution, like time evolving with this Hamiltonian, whereas we're applying it instead to approximating ground states, but it's the same idea. This other idea is to omit all of the 1-qubit gates in your quantum circuit. Now, this might strike you as kind of funny because then you get a very different circuit and a very different final state. But the motivation is that the noise mostly comes from the 2-qubit gates. The 1-qubit gates have much less noise than the 2-qubit gates. And so in particular, the 2-qubit gates on the IBM quantum computers are all controlled knots. And so if you start in the state of all zeros, the controlled knots keep you in that state. And so you know what the outcome of the circuit should be. And so the method that's proposed in this paper is, so you measure the fidelity of this ideal state, and you use the fidelity to predict the damping factor. And then you assume that the damping wouldn't be different if you put the 1-qubit gates back in. And I said that's the same as assuming that the damping is independent of theta, because removing the 1-qubit gates, at least for our ansatz, is the same as setting theta to 0. And a slight modification of this is, instead of using the fidelity in the state, you could measure your observable in that state and see what the damping is. And then here's method 3, which is the one that we proposed. So suppose that the thing that you're measuring is a local observable, meaning that it acts on a small number of qubits that are adjacent to each other. Then you actually don't necessarily need to simulate all of the qubits in the system in order to predict the expectation value of that observable. You only need to simulate the qubits that are in the backwards light cone of that observable. And here I'm borrowing, well, I'm not inventing so this term comes from relativity, and I'm also not inventing its usage for quantum circuits. This is sort of a standard terminology. But it refers to the fact that, like, if you're, for example, if you're measuring an observable on this qubit, then only the qubits that are in this cone that I'm drawing affect that measurement. And so you only need to simulate those qubits. And the advantage that this gives us is that even for arbitrarily large number of qubits, you can simulate shallow depth ansatz as long as you're measuring local observables, and the ansatz is also local.
Is this applicable irrespective of the type of many qubit state you have? For instance, if you have, I don't know, some long range entangled state,
yeah,
can you figure out the state of the, can you figure, I mean, is measurement of just the qubits nearby sufficient? It sounds like it would have some condition.
well,
Quite a bit of constraint, it seems, isn't it?
yeah, I mean, so
So when is this valid? When is this an okay thing to do?
there are two criteria that need to be satisfied.
Mhm.
One is that the observable is local, the thing that you're measuring.
Mhm.
And the other is that the ansatz is local. So
In other words, if a state is defined by a non-local observable, such as some, I don't know, topological state, then because it cannot be detected by a local observable, this wouldn't help.
That's right. If you need to measure all of these qubits simultaneously, then you can't use this light cone to help you.
I see.
But for the Hamiltonian that we're studying, the terms all act on at most 1 or 2 qubits, at most 2 qubits, and so that Hamiltonian is local.
Right. No, even if the Hamiltonian is local, you can have long range entangled state or some topological state. Toric code Hamiltonian is local, right? Hamiltonian being local does not guarantee the ground state does not have long range entangled properties that requires knowing, large number of qubits.
Sure. So you could find the ground state this way, but you wouldn't be able to measure those long range observables.
Right. You wouldn't be able to tell that you have the ground state you intended.
Well, you could tell that you had the ground state by measuring the energy, but not by measuring these other observables.
Well, you would always know that you reached the lowest energy state you can of a given Hamiltonian, but the whole purpose of simulating is to find out what that state is.
Well, the purpose of simulating is to measure observables, and I mean, in real life, most of the observables that we're interested in are local to some extent.
Anyways, but that's a what you're that's a matter of one's taste, I suppose. But I was just curious because everything would have fine prints and applicability conditions. Like when is this a fine thing to do, right? So
yeah,
that was
I
my
agree.
curious. Yeah. All right. Thank you.
And also, many Hamiltonians are not local. If you have a fermionic Hamiltonian, then it's often not local in terms of qubits. And so that would also, this also wouldn't apply for that. But so it applies for a specific set of things that we happen to be interested in the test problem that we're using.
Can I ask a quick question?
Yeah.
What's that's the slope of these lines that you've drawn?
Oh, so let me slow down a little bit and erase this. So all I'm doing when I drew those lines is I'm just saying, okay, so I want the pen. So let's say we're measuring this qubit. We just want to know, like, we're starting here and we're going to go backwards. We want to know at each layer which qubits affect that measurement. So right here, just this gate affects it, and then we go back and we see, oh, these qubits are now connected, and so this qubit and this qubit are going to connect it, are going to affect this measurement.
Yeah.
So now we have these two. And then if we go back another one, now these two qubit gates connect this qubit and also this one. And so now we have this.
I see. So this is not like a fundamental property of the quantum device. It's a property of the circuit that you've drawn.
Oh, exactly. Yeah,
Right. Okay. Makes sense. Thanks.
great. So now we want to benchmark these different methods, see how well they work, and compare them with each other. And to do this, we're going to use the following test problem. We're going to look for the ground state of this mixed field Ising model. And in particular, we're going to pick hx to be 1.5 and hz to be 0.1. And the reason for picking those particular parameters is that they're outside of a perturbative regime that we're using for method 1, which requires having a perturbative regime. So this Hamiltonian has several different perturbative regimes. One of them, of course, is just small hx, in which case the Hamiltonian is diagonal, or when hx is 0, then the Hamiltonian is diagonal on the computational basis. Also, if hz is 0, then you get the transverse field Ising model, which you can solve by doing a Jordan-Wigner transformation, writing these in terms of fermions, and then you get a quadratic Hamiltonian in the fermions. And of course, it's also solvable for large hx, in which case it's just diagonal in the poly x basis. So this actually has like 3 different perturbative regimes. And I've compared them here. So you can see that the blue is the exact ground state. The orange here is the small hx perturbative regime. And here I'm writing the energy to second order in perturbation theory for each of these expansions. And I also put it for the 2 other perturbative regimes that I mentioned. The only thing I want you to take away from this plot is that, so I'm going to focus on the small hx perturbative regime. And you can see that we can use that perturbative solution when hx is less than 1, and the perturbation expansion doesn't converge when hx is much larger than 1, and in particular, it doesn't converge for hx equals 1.5. So that's why we choose hx to be 1.5 over here. And then for method 1, we're going to pick, where's my pointer? We're going to pick hx in 0.1, 0.2, 0.3, 0.4, and 0.5, and measure the damping factor at these values of hx, average them, and assume that that's the damping factor when we go outside of the perturbative regime to hx equals 1.5. Now we could approach this perturbative regime, or sorry, we could approach hx equals 1.5 from both sides because we have multiple perturbative regimes, but that's not a generic feature. I mean, Hamiltonians that have a perturbative regime don't generally have multiple perturbative regimes, and so we're not going to do that. We're just going to use this one perturbative regime to try to predict this damping factor. And another little piece of information for you is that this ansatz that we've chosen, which is this ansatz, can represent the ground state of this Hamiltonian very well. You can get very close to the ground state with 7 layers. But we're going to go to much deeper circuits than that. We're going to go out to 50 layers. And the reason for doing that is because we're primarily interested in these error mitigation techniques. So even though you only need 7 layers, we're going to go out to 50 just so we can see how well the different error mitigation techniques work. And then another question, which I've kind of already hinted at, is, well, do we need to do error mitigation during the optimization phase or just at the end? And so all of these plots that you see here are VQE run on an actual quantum computer, and we're not doing any error mitigation. So the blue dots that you see are the actual output of the quantum computer. That's what we're feeding into the optimizer. The yellow dots are the exact evaluations of those same circuits, and you can see that they're approaching the minimum. And the exact minimum is also shown. And so that means that here, at least in this case, we don't need to do error mitigation during the optimization phase. Another way of saying that is that the effect of the noise didn't significantly shift the location of the minimum in parameter space.
I have a question.
Yeah.
Does this is now, does the fact that the energy reached minimum guarantee that you actually have a ground state of I presume is the ground state of this Hamiltonian known? I suppose you can do a classical like ED to know actual ground state.
Yes.
Right. So
Yeah.
now the fact that the energy is the same, does that guarantee it is the same state?
Well, I mean,
because energy is the same too within some resolution.
Yeah,
right? Some within some
yeah, it depends.
There's some difference.
It depends what the gap is, and you can see we're not exactly getting to the ground state energy, and so we're not exactly producing the ground state. We're producing some state which I would presume has large overlap with the ground state, but we didn't actually compute that overlap.
Can you compute the overlap?
Well, we're also running these circuits on classical computers, so you could easily compute the overlap on the classical computer. You couldn't do that, like, if you weren't also doing this classically, you wouldn't know what the ground state was, and so you couldn't compute that overlap. But we're only doing 20 qubits, so we could do that, but we didn't.
I think that's an important element of important sort of test of VQE result when possible. How much can we rely on energy? Because energy is always available. It's great if energy is reliable, but
Yeah.
I don't know how much we can rely on energy alone.
Yeah, I mean, it depends what the gap is between the ground state and the first excited state. I don't know, but so I don't have a lot more to say about that. It's true that we didn't converge all the way to the ground state, so there was overlap with excited states. And I mean, the purpose of this paper is not to show that we're not really testing VQE in this paper, we're testing error mitigation. I mean, VQE is kind of the test problem that we're using to test how well our error mitigation techniques are working. So all I'm trying to show from these plots is that we're getting close to the ground state energy without applying error mitigation during the optimization phase. But yeah, that's a good point that you raised. Another thing that I'd like people to take away from these plots is that the damping factor, which is the ratio between the blue dots and the yellow dots, is not constant. you can see it's increasing here, and it's increasing here. And this indicates that the damping factor is not completely independent of the point and parameter space, which is kind of a mark against method 2 that I showed you before, which assumes that it's independent of the point and parameter space. Okay. And then these are just the same plots, but from a different quantum computer. So now I only have this slide and the next slide. Those are the last slides with new information on them. And these are the most important slides too. They have our results on them. So here we're comparing all of these different methods for estimating the damping factor, estimating the, well, actually, let me back up and say, so here we're, one of the takeaway from these slides was that we don't need to do error mitigation during the optimization phase. And that has an asterisk on it, and I'll come back to that later. But for now, let's say the thing that we're mostly interested in is doing error mitigation once we have the optimized ansatz. And we just want to correct the expectation value of the observable in the optimized ansatz. So the ansatz that I used to make, that we used to make these plots were all tuned classically. So now here's the damping factor as a function of the number of ansatz layers. So that's the depth of the circuit. And the x's are the measured damping factors. And so you can see it's pretty much decaying exponentially. That's close to a straight line on this logarithmic y-scale plot. And so the method that we proposed of estimating the damping factor using this exponential fit is working pretty well. So these x's go out to 15 layers. And so we fit an exponential to these, which is this yellow line. And then out here, those are all predictions, and you can see it's matching fairly well. Over here on the other quantum computer, it didn't do quite as well out here, but it did work out to like 30 layers before weird things happened. So it still let us extrapolate a bit. So then that was method 3. Now, method 1 was the one where you use the perturbative regime. That's the blue line. And you can see that's also working pretty well. And that actually captures this part here where it diverges from the orange line. So measuring the damping factor from the perturbative regime is working pretty well, but it still goes pretty wrong over here and over here. So it's also not perfect. Actually, I guess we didn't. Well, you can see over here, it didn't get that one. And then method 2, the one where you eliminate all of the 1 qubit gates, that's the 2 versions of that are these other, the green and red lines. And you can see that those are not working as well. They kind of diverge away, which you might expect because they assume that the damping factor doesn't have any parameter dependence, which it does. And now here's another way of visualizing those results. So in these figures, 3 means that if we were to use that estimated damping factor to correct the energy, would we get, or to correct the expectation value of the observable, which in this case is the energy, would we get within 10% of the correct value? So 3 means that, yes, we succeeded in getting within 10%. 2 means that it wasn't statistically significant to 1 standard deviation. 1 means that it wasn't statistically significant to 2 standard deviations, and 0 means that we failed to mitigate it to within 10%. And without any error mitigation, you can only go out to about 4 ansatz layers. Whereas these methods all extend the circuit depth that you can tolerate pretty significantly. And with the best performing of these two methods, which are these two, the one that uses the perturbative regime and the one that uses this exponential fit in the number of layers, they let you go out to about 25 or so ansatz layers, which again is a significant improvement over what you could do before. But also in this case, it's classically simulable out to 15 or 17 or so ansatz layers because of that light cone argument that I gave. So this is extending a little bit. Well, this is 20 qubits, so any number of layers is classically simulable. If we imagined that we had more qubits so that it weren't classically simulable, then 25 layers would be a little bit beyond the classically simulable regime. And so we can imagine that there might be some problem for which this lets a quantum computer be useful. We're still looking for that problem. If you have any ideas, that would be great. And another point which I said I would come back to is that we didn't apply error mitigation during the optimization phase. In fact, some of these techniques wouldn't work during the optimization phase. They wouldn't really make sense except once you have the optimized circuit. And so is it okay to not do error mitigation during the optimization phase? Well, it was for this Hamiltonian. And I think the reason for that is that the terms in the Hamiltonian all have about the same size. They all act on 1 or 2 qubits. But if instead, if we have the following Hamiltonian, something like minus the sum over I zi, maybe I should have specified earlier, but whenever I write zi or xi, that's like poly z and poly x. Let's say plus j times x0 through x n minus 1. So I did a little experiment with this one, and what I found was that the damping factor for this term was something like 0.2 when I ran it on 12 qubits, and the damping factor for this one was like 0.6. And so in this case, the damping effectively changed the value of j, and so the ground state depends on j, and so you would effectively see a different ground state because of the damping, and so you couldn't do the optimization without some sort of error mitigation that compensated for that. So another thing that one might want to think about is a way of dealing with situations like this, or one could stick with Hamiltonians that don't have terms of drastically different size and try to use these techniques. Okay, so that's all I have to say. I think we succeeded in benchmarking some of these methods and showing that they can be useful, but there's still a lot of challenges ahead towards the goal of making quantum computers useful for solving physics and chemistry problems, and this work has helped us understand a bit better what those challenges are and how we'll continue to chip away at them.
Thank you, Eliott. If I may ask another question, what is the takeaway message? You compared 3, and it sounded like 1 out of 3 was a clear loser.
Yeah.
And you were kind of careful in not declaring winner or loser of the remaining 2, 1 being yours.
Yeah.
So what should we take away? What should we remember as a ultimate outcome of this comparison exercise?
Yeah, so which of these methods you apply depends a lot on the situation. So for example, this method 1 over here, you can only apply when your Hamiltonian has a perturbative regime. And of course, not all Hamiltonians have a perturbative regime. Whereas method 3 here, you can only apply when your Hamiltonian is local and your ansatz is local. So those are kind of different scenarios where you might be able to use these methods. And I guess the goal of this paper, I mean, it wasn't as much to say, okay, here's the like error mitigation technique that works best in all situations. Instead, it's like trying to get an idea of how deep we can make our circuits. Like, I
So
mean,
can you give us an example of a Hamiltonian which does not have perturbative regime
oh, sure.
and the answer is not known, like the ground state is not known, you know, it's something that we would like to solve and does not have a perturbative regime?
Yeah.
What could that be?
So one example is the SYK Hamiltonian.
Okay,
I mean,
but it's exactly solvable by hand.
it's
You don't
exactly
even need a classical computer.
It's exactly solvable in the large n limit by hand. And yeah, it's large n limit, and it's exactly and you can diagonalize it for like very small n, but there's also an intermediate range. And so it might be useful to study SYK without taking the large n limit. And these are all 4 Majorana fermion interactions, and so it doesn't have a perturbative regime. Actually, there's another thing we do when studying SYK analytically is we take the ensemble average. There's the random coefficients, the JI, JKL.
Right.
And you always take the ensemble average over those things. So you might be interested in studying a particular instantiation of SYK rather than the ensemble average. And so that's another problem which we don't have an analytic solution for. But you could in principle study on a quantum computer. You'd have to worry about this noise. And in
I
that
think
case,
without the ensemble average, it stops being SYK.
that's true.
SYK, right?
It's
SYK is defined by the whole ensemble average,
that's
reducing the randomness and the underlying ensemble average. Ensemble is key aspect of the. Otherwise, each realization that you might consider as one example of infinitely many SYK would be very special. It would be specific to that that case, right?
Yeah.
So you're not going to be able to learn something that has universal information, insight to give.
Well, you might.
So,
I mean, I was talking to, Amir, so Tom's student Amir, and there are some outstanding questions about whether certain properties hold for like generic instantiations of SYK versus they only hold in the ensemble average. So it's still an interesting thing to study.
So have you tried to simulate SYK at finite n, like n of 7? I think you can.
Yeah.
You can do ED up to what, 4, 5?
Oh, much larger than that.
Right.
So remember also that like the n in SYK is the number of Majorana fermions, and there are like 2 Majorana fermions per qubit. So like n equals 40 SYK is 20 qubits. And yeah, you can go to like 60 or so fermions on a classical computer. And yes, I've tried simulating SYK on a quantum computer,
Mhm.
but there are a lot of additional challenges with that. So that's a more difficult.
Like
Oh,
what kind of challenges?
there are a bunch of them.
If you wouldn't mind sharing.
Yeah, let me make a whole new list here of challenges for simulating SYK. So challenge 1, there are lots of terms. So
Mhm.
there are n choose q terms. And we often pick q equals 4 because that's the smallest q for which this is, which this has a holographic dual. So that's a lot of terms, and you have to, whenever you measure the Hamiltonian, you have to measure all of the terms in sequence. So
Mhm.
that just makes it, there are a lot more circuits that you need to run in order to measure, in order to take one measurement of the energy.
Mhm.
Whereas for this Ising model that I showed before, the number of terms is just order n instead of n to the q. So that's one challenge. Challenge 2 is that the terms are all non-local, or the terms are generically non-local.
Right,
They're
because
these,
they have all range interactions.
well, not only that, that's part of it. That
Mhm.
makes them non-local in like the fermion space, but then you also have to do Jordan-Figner or Bravai-Kitaev, and that makes, and they're also non-local in the on the qubits. And in particular, they can act on like many qubits at once. I actually made some histograms of like the sizes of the different terms in the SYK Hamiltonian when you write them either using Jordan-Figner or Bravai-Kitaev, and Bravai-Kitaev does somewhat better than Jordan-Figner in terms of like keeping these terms not acting on too many qubits at once, but it still gets very large when n gets large. So you have to measure lots of qubits simultaneously, and you have to measure qubits that are separated from each other by a lot simultaneously. And so that leads to a lot of noise, especially because, as I mentioned,
Wait. Then is the SYK a problem that is not accessible by either of the methods?
that's right. Yeah,
Huh.
you couldn't use either method.
I was looking for a problem where only your methods can do. Trying to be supportive.
Well, you could probably write down some Hamiltonian that's local but doesn't have a perturbative regime.
Yeah, but that won't be, you know, if you go into a cave and cook up something that nobody ever thought to be interested in, it's kind of hard to convince others that is the important thing to solve, right? You want to find something that is already kind of recognized to be an important problem and only your method can handle. That's kind of ideal. If possible, of course, you know, in life you never get everything you want, but ideally that would be great. Yeah.
I'm also not really partial to my own method. It just, I think if a different method works better, then we should use that one. But yeah. Yeah, so as I said, the second problem with simulating SYK is that the terms are very large and non-local, and that leads to challenges because, as I showed you over here, at least on these IBM quantum computers. Now, it would be different if, so these IBM quantum computers are like superconducting transmon quantum computers. If you were using a different type of hardware, for example, if you're using trapped ion quantum computers, it would be different. But for these transmon quantum computers, the readout error rates are very high. You can see that here, the max we have here is like 28% readout error.
Mhm.
And often more typical readout errors are like 5% or so, which is still very high. And so now if you have SYK on n qubits and you need to measure like order n or order square root n or something qubits at once, you're talking about really high readout error rates because these get compounded. So you have very, very small fidelities. You need to do some really good readout error mitigation if you want to simulate SYK. Or at least if you want to measure the SYK if you want to measure the Hamiltonian. So that's problem 2. I'll call that term size. And then problem 3 is the ground state is very complicated because you have so many terms and you have these all-to-all interactions among Majorana fermions. And so a ground state, like this ground state that I drew over here, is really good for representing like the ground state of the 1D mixed field Ising model. You only need like 7 layers to get a pretty good approximation of the ground state. But it's not a good ansatz for finding the ground state of SYK. At least, I mean, in principle, this ansatz, if you make it arbitrarily deep, it can become a general unitary and could represent any any state. But
can you try starting from a known ground state of, say, I don't know, infinite n or smaller n? Because there are 2 limits where we know the answer. Infinite n we can solve on piece of paper. Small n we can do ED.
Well, infinite n we don't know for a particular instance, and we're always going to be running a particular instance of SYK on the quantum computer. Small n, yeah, you could diagonalize that exactly, but you still have to construct a quantum circuit that puts you into that state, and that's not trivial.
You cannot initialize in that state.
No, the quantum computer always starts in the state of all zeros, and then you have to apply gates to put it in other states.
That's just because IBM sets it up that way, isn't it?
Well, also because these qubits start not entangled. So they start out in some product state. And also 0 is like physically the lower energy state for these qubits. So if you just let them thermally relax, then they'll go into the state of all zeros.
I see. Cool. Very cool.
So that's another challenge, is ansatz depth. And this is something that we haven't actually tested explicitly, but you might say, well, maybe the reason why this ansatz is so bad at representing ground states of SYK is because it only has these local interactions. SYK is non-local, maybe we want some non-local ansatz, and that would be able to represent it better. But then you're limited by the connectivity of the qubits, which I don't remember what slide that's on, over here. So the qubits only have these particular connections. And so you can't really do any arbitrary ansatz that you'd like without adding extra depth to your circuit. That would also be different on a trapped ion quantum computer because trapped ion quantum computers do have all-to-all connectivity.
Right.
So those 2 things are both like reasons to think that maybe trapped ions would be better, but trapped ion quantum computers are currently smaller than these superconducting quantum computers, and we'll just have to see.
Also, they are slow. So if you want to for
Yeah.
some reason. I mean, if you want to say that I've done SYK something, the first thing you'll be asked is, okay, so how does that compare to large N limit? And when somebody says, how does it compare to large N limit, they have the ensemble average in mind. So you would have, in order to benchmark, you would have to do some ensemble average. And with IonQ being very slow, that would be difficult.
That's true.
But
yeah.
well, that was very interesting. Thank you so much for sharing. I think these kind of like learning how things fail is one of the really it's what make this kind of casual meetings precious, because it's really important, but it's not published. You know, you don't publish. I've tried 20 different things and they all failed in this many ways. So journals don't like it.
Yeah, that's true. I mean, I mean, I don't know if Paul's still on here, but Tom could tell you that. Is Paul still on here? I guess not. Tom could tell you that I spent a long time like studying SYK, and actually one of my A exam questions was about SYK, and I spent a long time studying it. Like, exactly.
No, I believe you. And when we started talking about SYK, you got actually excited.
Oh, yeah.
Because you spent a lot of time, you had a lot to say.
Yeah, so I spent a lot of time studying SYK.
Yeah.
And
Yeah.
then these things all fail for this reason. So,
yeah. Life is so tough and interesting. Yeah, very interesting. Well, thank you so much. All right, I gotta get going. Are there other questions? No, but I kind of hijacked and monopolized questions. Are there questions, people? Well, if any question come to your mind later, make sure when you email to Eliott, 1 L and 2 T. Otherwise, it goes to wrong person, wrong Eliott.
yeah.
All right. Well, thank you, everyone. And we'll meet back with another speaker next week. Have a nice rest of the week, everyone. Thank you, Eliott.
Oh, you're
Bye.
welcome. Bye.